As we study chemical systems, one of the important things to keep track of is the changes in heat energy or temperature of the system. We can learn a lot about reaction systems by studying how heat is transferred to and from systems. We can learn which species are more stable, which ones are higher energy, and of course this has a lot of implications for us and for everything that we do. When we talk about heat and temperature, these two terms are closely related, and they're related to what we call the internal kinetic energy of a substance. Now, any substance is made up of atoms of some sort, and we could start by looking at a solid. Now, if we were at absolute zero, all of the particles in the solid would be rigidly still. However, as we begin to heat the system up, those particles will begin to vibrate back and forth just a little bit. They'll begin to shift around. You could sort of think of people in a classroom. You could have everyone in their seats, but there's still motion going on. People are moving back and forth, adjusting, shifting a little bit. That's the same sort of thing here. Even though everything is held in place in a solid, everything is vibrating a little bit. The more you increase their kinetic energy, the more heat energy you add, the faster they vibrate. Eventually, they're going to begin to vibrate fast enough that some of the particles will begin to break out of the solid matrix and move freely about. Now, they're still close together, and this is a solid to liquid transition. As we continue to add heat energy, they vibrate faster and faster, move faster and faster. Some of those particles are going to get enough energy that they are going to be able to escape out of the liquid and into the gas phase. This is the liquid to gas transition. So when we talk about phases, solid, liquid, gas, we're talking about the amount of kinetic energy that the particles within that substance have. Now, there's two terms that we can use in relation to this. One of them is temperature. Temperature we define as the average kinetic energy of the atoms or molecules that make up an object. The other term that gets used is the term heat. And heat refers to the amount of energy that can be transferred from a hotter object, that is, an object having more kinetic energy, to a cooler object, an object having less kinetic energy. You can sort of think of heat and energy or heat and temperature in terms of wealth. Let's say that we wanted to take a collection for a good cause. Well, if everyone has $5 available that they could give, that's kind of the average amount. However, the total amount that would be available is going to depend on how many people are present. If you have 10 people and they have an average of $5, you're going to have $50. If you have 100 people with an average of $5, they're going to have $500. Temperature is independent of the number of particles present. Temperature is just the average energy. Heat energy is more like the total energy available. That's going to depend on the number of particles or the amount of the substance that is present. We can measure heat with a couple different units. Two of the most common are the calories or the joules. Now, 1 calorie with a little c is the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. By the way, one little factoid, in nutritional circles, you'll see the calorie with a capital C. 1 calorie with a capital C is equal to 1,000 of the little c calories. A capital C calorie is really a kilocalorie, and that's sort of some shady marketing, I think. And we will not use that term in this class because it's ambiguous. The other term that is related is the term joules. And 1 calorie is equal to 4.184 joules. So if it takes 1 calorie to raise 1 gram of water 1 degree Celsius, it takes 4.184 joules to do the same thing, raise 1 gram of water by 1 degree Celsius. Finally, let's mention briefly the temperature scales. There are three commonly used temperature scales. The one that you're probably most familiar with if you're from the United States is the Fahrenheit scale. The Fahrenheit scale is a traditional scale where you have the freezing point of water at 32, the boiling point of water at 212, and absolute zero, the point at which particles have no kinetic energy, at minus 459. This is a kind of a classic scale, but in most countries it has kind of gone gone by the wayside in favor of the Celsius scale. The Celsius scale says, okay, let's set the freezing point at 0 and the boiling point at 100. Now, one thing to notice here, if you look at the gap between the freezing and boiling point, we have a gap of 180 degrees Fahrenheit between freezing and boiling temperature. On the other hand, we have a gap of only 100 degrees Celsius. What this means is that a degree Celsius is a bigger unit than a degree Fahrenheit. Now, the last one that we're going to use is Kelvin, and this is not referred to as degrees Kelvin, but simply Kelvin. Kelvin sets absolute zero at 0, and then sets the freezing point at 273. Now, notice that a Celsius degree is the same size as a Kelvin degree. The gap between 0 and 100 is 100. The gap between 273 and 373 is also 100. Kelvin is particularly useful when we're working with gases, but most of the time we'll use Celsius. However, all three are in use. Kelvin most commonly in scientific circles, Fahrenheit and Celsius just in different parts of the world. So it's important to be able to calculate and interconvert between these. In order to interconvert, one of the things you can do is to use an equation like this. You should know how to use these formulas. I'm not going to work any examples here, but I think that you'll be able to work these out. I encourage you to practice one or two, make sure you can do this conversion. These relationships will be given to you on the test, and you'll probably have maybe one question involving interconverting between these.